So I mentioned the term stereoisomers, and these are isomers that have the same basic structure but different geometry, different, a spatial arrangement of the atoms. And we already introduced the term enantiomers, which are mirror images of each other. The other term is diastereomers. Diastereomers are stereoisomers that are definitely not mirror images of each other, okay? So maybe two OHs are facing the same way and then another one is facing a different way. So you can't call them mirror images. Cis-trans isomers back in the alkene chapter and the cycloalkenes, those are considered diastereomers. The epimers is another term. Epimers, those are isomers that differ in just one carbon. And galactose and glucose are epimers. They differ in carbon number 4. Okay, so those are just two terms I wanted you guys to write down. Now let me show you what galactose looks like. Galactose, like I told you, is part of lactose, which is a disaccharide, and that is milk sugar. Galactose is also an aldohexose, just like glucose is. And this would be the structure of galactose. This is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. Carbon number 1 is pointing to the right, just like, carbon number 1 is the aldehyde. Carbon number 2 is pointing to the right, just like glucose. Carbon number 3 pointing to the left, just like glucose. And this is where galactose differs from glucose. Carbon 4 is also pointing to the left. And then carbon 5 and then carbon 6 is not chiral, so it doesn't really matter. Okay, taking a look at this, is this D-galactose or L-galactose? How do you know? You look at the highest number chiral carbon, the one that is furthest away from the aldehyde group. So this is carbon 1, 2, 3, 4, 5. Carbon 5 is the highest numbered chiral carbon. The OH is pointing to the right, so therefore this is D-galactose. Okay, so if you know, there you go. If you know the structure of glucose, you pretty much know the structure of galactose because it looks just like glucose, but you flip carbon 4 to the left in a D-galactose. If this was L-galactose, what would happen? All the chiral carbon OHs flip. So you would have, I'm just going to go ahead and draw it right here, carbon 2, the OH would be this way. Carbon 3, the OH is this way. Carbon 4, this way. Carbon 5, this way. And then remember, carbon 6, it doesn't really matter. It's not chiral, so you can just condense it. This over here, this would be L-galactose. Why L? It's a mirror image of this. They're non-superimposable, but it's a mirror image, meaning that everything to the right here is to the left there. Everything to the left here is to the right there. The furthest chiral carbon, the one that has the highest number, number 5, pointing to the left, therefore it is L. Okay, so that's the second hexose that you need to know. And then the third hexose is a ketohexose, and that is fructose. That is fruit sugar, fructose. It's a lot sweeter than galactose and glucose. Fructose is a ketohexose, and remember, ketones can never be at carbon 1, so the ketone here is at carbon 2. So let's take a look at what fructose looks like. This is carbon 1. Carbon 1 looks exactly like carbon 6. It's not chiral. This is carbon 2. And then the way I remember fructose is that carbons 3, 4, and 5 look exactly like glucose. So in glucose, the OH was pointing this way at carbon 3. At carbon 4, it was this way. At carbon 5, it was this way. And then carbon 6, remember, is not chiral. So this is fructose. Let's determine if it's D or L fructose. You look at the furthest chiral carbon, the one that has the highest number furthest away from the carbonyl group. This is chiral, this is chiral, this is chiral, but this one is the highest numbered one. It's number 5. This one's not chiral. It's pointing to the right, so therefore this is D fructose. Obviously, if you're working with L-fructose, everything's reversed. So this would be on this side, this would be on this side, this would be on this side. You should be able to draw that in your notes. Okay, so those are your monosaccharides that you need to know. Glyceraldehyde, dihydroxyacetone, ribose and deoxyribose, glucose, galactose, and fructose. These are all Fischer projections, open chain Fischer projections, okay? Now, in order for us to create the disaccharides, we need to learn how to do a Haworth projection, which is closing it to form a ring. Do you guys remember back in the, I think it was the alcohol chapter, was it, or was it the aldehyde chapter? Maybe the aldehyde chapter, where the term hemiacetal was introduced. I think it was the aldehyde chapter. A hemiacetal is a reaction between an aldehyde and an alcohol. And when the aldehyde group reacts with the furthest chiral carbon alcohol, it closes the ring and forms a hemiacetal, and that's the Haworth projection. So, and that's the only way we can move on into disaccharides. So let me just quickly show you how this is done. It's a little complicated, so it's unlikely you're going to see questions about it. I just wanted to show you how the ring closes, because I remember when I was a student, our professor just basically put a Fischer projection on the board, and then all of a sudden it became a Haworth, it became a ring, and I had no idea how he went from one to the other. So for those of you who want to know every single detail, the way I was when I was a student, let me show you what's going on. All right, so this is glucose. I'm just going to do glucose, show you what happens. So by now, you will have practiced drawing glucose enough times, so this is all a piece of cake. All right. This is D-glucose, all right? So in order to create our hemiacetal, you're going to have this aldehyde group reacting with carbon number 5 alcohol. So you're going to have this become the ring. And then this carbon number 6, this is number 6, is outside of the ring. So you're going to create a ring between carbon 1 and carbon 5, a hemiacetal ring. All right, let me show you how that is done. I'm going to try to squeeze it in here, okay? So this is going to be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6, all right? Now, carbon 1 is an aldehyde, so we're just doing that. Carbon 2, now anytime an OH group is pointing to the right, point it down on the ring, okay? So carbon 2 is to the right, it's going to go down on the ring. I'm going to ignore the hydrogens. I'm just going to focus on the OHs right now because they're the ones that really matter. Carbon 3, you notice it's going to the left. So if it's going to the left and the open chain, it's going to go up on the ring. So carbon 3, OH is up, okay? Carbon 4, this is, here's a 1, 2, 3, 4. Carbon 4, it's to the right, so it's going to be down. Remember, right, down, left, up. So this is going to go down. I'm just going to put it outside here. You can put it inside the ring. It doesn't really matter. Okay, so this is up. All we care about right now is up and down. Okay, I'm trying to oversimplify it, but it works this way. Okay, and then carbon 5, this one's 5. It's to the right, so it's going to be down. And then carbon 6 is outside of the ring. So we'll just condense it like this. All right, so what's going to happen? Again, this is an intro biochem class. You don't need to worry about mechanisms or any of that. But I'm just going to show you, again, if you don't catch it, it's okay. I guess you can watch the video over and over again, but no worries. All right, it's unlikely you get asked questions about how the ring forms. The double bond is going to break. The electrons of the double bond. They go towards the oxygen here. Oxygen becomes super electronegative. It pulls this hydrogen. See this hydrogen on carbon 5? Pulls it over here. Okay? So the hydrogen goes over there. All right, so now what happens? This carbon has 3 bonds. It wants one more bond. This oxygen has 1 bond. It needs 1 more bond. Remember, oxygen always has 2 bonds. So I want to make it look like a hexagon. In reality, it looks more like a boat or a chair, and you can read about all of that, but I'm just going to make it into a nice Hayworth hexagon. So I'm going to just scoot this oxygen over. So this is the oxygen that used to be the OH of carbon 5, and there you go. You've just created a Hayworth projection for glucose, okay? And then the next video, we will talk about alpha glucose and beta glucose. Okay?